So before we begin to speak about the differences between the first order and the zero order, we need to first establish a common ground. And this common ground is that both the words first order and the words
zero order
both refer only to the rate of a reaction or a specific process, be it elimination of a certain chemical, absorption of a chemical, etc., etc. So both of these only refer to the word rate and nothing but rate. What's the differences between the first order and the zero order then? So let's start with the zero order one. It's much more simple. So if you were to have this graph, and this would be your y-axis and this would be your x-axis. A zero order, or one that is a decreasing zero order, would look something like this. It's, well, linear. And as with anything, as with any graph that is linear, it can be described by the following equation, where y is equal to the slope multiplied by x plus a constant. And this constant can also be referred to as the initial starting point on the y-axis, or the y-node. So let's say, for instance, that the y-axis represents the plasma concentration, or the concentration of a given drug in the plasma, while the x-axis represents the time. In this case, let's do a little bit of a reorganization of this equation here, where you get the plasma concentration at any given time or at a specific time is equal to the slope multiplied by the x-axis, which is the time, plus the initial plasma concentration. So, okay, you have the time from the x-axis, you have the initial plasma concentration, which is on the y-axis, and also the plasma concentration is the one that you are planning to get from this equation. So what is the m? What is the slope? The slope, as you remember, is, let's say for instance, let's choose any 2 points on this graph. So let's choose this point here and this point here. y1, y2, and also this is its corresponding point on x-axis, which is x1, and also x2. And the slope, as with any other slope, is equal to y2 minus y1 over x2 minus x1. So the slope here is equal to this. And in the zero order reactions, this is also equal to the rate, and is also equal to the constant. So let's say, for instance, that this was an elimination graph of a specific chemical. Let's say, for instance, alcohol. It does show a zero order graph. The elimination constant of alcohol would be equal to the slope, which is also equal to the rate. Because as you can see in this graph, the rate is constant. So let's say from here to here, that's the difference of a difference of 2 milligrams. And from here to here, that's a difference of also 2 milligrams. So after 1 hour, your body gets rid of, let's say, 2 milligrams. And after the second hour, your body also gets rid of 2 milligrams. And after the third one, also 2 milligrams, and so on and so on. Let's say m here can be replaced with the letter k, which is the constant of this specific process for this specific compound, or the rate. First order, on the other hand, is a more of an exponential graph. So if this were your y-axis and this were your x-axis, you'd have a graph that looks something like this. And this is an exponential graph. How do you describe an exponential graph? How do you predict its points? It's simple. You make it linear. So how do you do that? So let's say this is your y-axis, this is also your x-axis, and this graph becomes linear. How is that? Let's take a look. So let's here you have 1 and 2 and 3. And here you also have 1 and you have a 2 and you have also a 3. And here, let's say at the first point you would have a 1, and this at the first point you would have a 1. And at the second point you would have a 2, but on this graph it would show a 10. Because this is a semi-logarithmic scale. So what's a semi-logarithmic scale? It's either a logarithmic scale or a not logarithmic scale. So a semi-logarithmic scale means that this scale is a normal scale, while this scale is a log scale. So what that means is Second point here is 10, and the third point is 100 instead of a 3, and the third point is 1,000. And the fourth point, try to guess it, and you guessed it correctly, hopefully. It's 10,000. And you get something that is a bit more linear. So there are two ways you could describe this equation. There is the easy way and there's the less of an easy way. So let's start with a much more easier way. And this is the only one I'm going to cover, by the way. So you have here y is equal to the slope multiplied by the x-axis plus a constant. And this is also a y is also equal to the slope multiplied by the x-axis plus the initial point on the y-axis, or the initial plasma concentration in this course. But keep in mind that this is not a normal scale. This is a different scale. This is a log scale, meaning that this is a log of y equal to the slope multiplied by the x, because the x-axis is a normal one, and plus the log of the initial plasma concentration, or the initial point on the y-axis, this one. Let's get the slope here, and the slope is the same as this slope, but also keep in mind that the y-axis is not a normal scale. Instead, it is a log scale, meaning that this would be equal to the log of y2 minus the log of y1 over x2 minus x1. And unlike the zero order reactions, this is not equal to the constant, or this constant, the k here. Instead, to get the k, you need the following equation, where the slope is equal to k over 2.303. And this is the k that we've been speaking of. This would be the elimination constant if this were to be an elimination graph, the absorption constant if this were to be an absorption graph. We don't care, because these only address the rate of a specific process or a reaction. So you can see here that the rate is not constant. So what is constant? The constant here is the t-half, or the time required to go from one concentration to half of this concentration. So let's say here you started off with a 4. So let's say you have a half-life, or the t-half of 1 hour. So after 1 hour, this would be a 2. And after a second hour, this would be a 1. And after the third hour, this would be equal to a half. So the t-half, or the half-life here, is the one that is being constant. So how do you calculate this t-half? How do you predict this t-half, or this half-life? And for this, you will need this equation, where the t-half is equal to 0.693 divided by the k, or the constant. Okay, so let's rewrite this equation in a bit of a different manner. So let's write that down here. So let's write that down here in this space here. So the y-axis is the plasma concentration. So the plasma concentration at any given time, so the Cp, the log of Cp, is equal to the m, or the slope, which is equal to the slope, which, as we've said, is equal to k over 2.303 multiplied by the x-axis plus the log of the initial plasma concentration. So this would be equal k over 2.303 multiplied by the time plus the log of the initial plasma concentration, or the C node. So now we know how to predict the half-life of this equation here, of the first order graphs. So how do you predict the half-life in zero order graphs? For this, you can use the following equation, which is in which t-half is equal to the initial amount divided by 2 times the k, or the rate in this part, the rate and also the slope. Okay, so what are good examples of the first and zero order reactions, and when can you really see them? So zero order reactions, you would see them in situations where you do not rely on diffusion. So let's say, for instance, you are giving someone an injection. This injection, or this IV bolus, is being injected by your very own hand. You are not depending on the diffusion between two different membranes. You are depending on how fast you push this plunger. You can also see this when the body's capacity of eliminating a certain drug has been reached. So one very important chemical that always shows a zero order graph is a good example of this is alcohol. when you drink a glass of alcohol, any wine or anything like this, your body has a very limited supply and can only handle about 8 milligrams of alcohol per hour. So the body gets really easily overwhelmed with this amount of alcohol that you're drinking. So it does show a zero order graph. Any other chemical where the body's capacity of eliminating this chemical has been reached will show a zero order. And this also means that at the end of any zero order reaction, there is, especially if it's an elimination reaction, there is a part that is a first order one, but this is usually negligible. So when can you see something like the first order one? You will see this. You will see the first order in most reactions, in most elimination, in most absorption where there is a diffusion. You would easily see, or you would almost always see, the first order rates. So let's say an absorption of a drug or elimination of any drug where the body's capacity has not been reached yet. Let's say drug A, you take 1 milligram and your body can filtrate about 0.5 milligrams per hour. You take 2 milligrams and your body can filtrate about 1 milligram per hour. And this is just a hypothetical example. You take 3 milligrams and your body can only filter 1.5 milligrams per hour. But let's say zero order or the body's capacity is reached at 3 milligrams or the plasma concentration of 3 milligrams. So then you go to 4 and your elimination rate remains at 1.5. And you take 5 milligrams and then it stays at 1.5 milligrams per hour. This is the end of this part of this video. Hope you liked it. If you did, please thumbs up, subscribe, hit the bell icon, and also don't forget to go to our website where you can find some handouts that should be good. Thank you for watching and see you next time.